we're going to talk about probability. We're not going to get really deep into probability, but we are going to talk about some of the basics. As we're looking at probability, what we're really looking to do is to come up with measures of chance. So how can I quantify how likely an event is? And I've got a couple of real classic examples of probability. There are lots of more sort of scientific examples, but I'm just going to stick with the more what I think are the more fun ones. We're going to roll some dice, we're going to look at some coins, and we're also going to take a look at just a standard deck of cards. So we're looking to measure the chance of something happening. I'm going to go ahead and start with just a simple coin toss. So we're going to toss one coin. If I toss that one coin, so I toss that one coin and then it shows up, and I know you can't see that. I never have quarters, so I only had this old nickel and pennies. So this nickel landed on heads. Well, this nickel could have landed on one of two things, right? That coin could have landed on either heads or tails. This is my sample space. So the sample space is the space of all possible outcomes. I'm going to call it S. It's the set of all possible outcomes. Well, there's my nickel. There's only two. It could either be heads or tails, and that's it. So my sample space consists of head or tails. If I want to come up with the probability of an event happening, so the probability, I got heads, didn't I, when I tossed that? So if I wanted to know what the probability of heads was, I would count up the favorable outcomes being heads or tails, and I would divide that by the total possible outcomes, so the total outcomes. Well, the probability of heads, and I'm starting with one that hopefully you know I had a 50-50 chance, right? So there's only one head in that sample space. It's only going to happen one time. So I've got one head out of the two. So that's the probability of getting heads. Well, we've got some important things here. We've got the sample space. We have, this is the theoretical probability formula. Really straightforward, though. Favorable out of total. And then I've got a probability. I have my probability represented as a fraction. You could represent this instead as a decimal. You could also represent this as a percentage, which would be 50%. Notice I didn't say 50-50. 50-50 is the odds. So we're not doing odds at all, so you don't need to worry about mixing those two up. So we're just doing the fraction, the decimal, or the percent. And if I don't specify, it doesn't matter which of the three variations that you choose. Okay, so sample space. What if I was rolling now a die? So we roll a die, just a regular 6-sided die. So I could land on 5 or 1 or 2. So I've just got a regular 6-sided die. So if I were to roll a die now, I can come up with that sample space, S, all possible outcomes. Well, the smallest outcome is a 1. I could land on a 1, 2, anything up to a 6, 3, 4, 5, 6. I can also talk about the number in my sample space. The number in my sample space, n, which is our same old n for how many we had in a distribution. So the number in that sample space is 6. If I go up here to my nickel, the number in this sample space is 2. And it's no coincidence that that shows up in our denominator. Okay, so let's take a look at some probabilities for this die. These might be a little hard to read, so I'll read them to you. The first one says, what is the probability that the die shows a 3? So I'm going to kind of cheat here and pretend like I'm rolling it, and then, well, look at that, it landed on a 3. Let me put my sample space up here. It was 1 through 6, 3, 4, 5, 6, and n was 6. So the probability that my die lands on 3, so I put my event in here, the probability of getting a 3, there's only one 3 up there. So there's one 3 out of the 6. So my probability is 1/6. If you wanted to represent that as a decimal, you would just go to your calculator and divide. I'm just going to leave it. What's the probability that it shows an odd number? So the probability of getting an odd number, well, now I go up here, and every other one's an odd. So I get a 1, a 3, or a 5. Now there's 3 possibilities. So I've got 3 possibilities out of the 6. You need to reduce these fractions. 3 out of 6 is the same as 1 out of 2, or 0.5, or 50%. Okay, how about this one? What's the probability that you get an odd number, so what I've circled, or a number less than 3? So the only number that I haven't circled that's less than 3 is that 2. I don't double count. It is true that there are 3 odd numbers, and that there are 2 numbers less than 3, that'd be 5 favorable, but that's not really the reality, right? I've got 3 odds, and I have already circled the 1, but I haven't circled the 2. So we don't double count in probability. So of my 6 outcomes, the ones that satisfy either an odd number or a number less than 3 are the 1, 2, 3, 5. So that would be 4 of them. So the probability of odd or less than 3 is favorable, which is 4, out of total, which is 6. And if I reduce that down, I would get 2/3. Okay, D. Now 2 dice are rolled. What's the probability of getting doubles? This is a much different problem than A through C. So I want you to kind of think this through. If I rolled 2 dice, I didn't get doubles here, I got a 3 and a 6. So as I do 2 die, I need to incorporate that I've got 6 possibilities here and 6 possibilities here. But we don't turn out to add them. We end up multiplying, and here's why. So on the first die, this is called a tree diagram. I can get anywhere from 1 to 6. 1, 2, 3, 4, 5, 6. Okay, so there's the first die. On the second die, I can also get anything from 1 through 6. But they're like attached to whatever I get on the first one. So if I get a 1 on the first die, I could get 1, 2, 3, 4, 5, 6 on the second one. If I get a 2 on the first one, I could match with that 2 any number on this red one, 1 through 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I'm not going to do all those. 1, 2, 3, 4, 5, 6 could follow a 3. 1, 2, 3, 4, 5, 6 goes with the 4. 1, 2, 3, 4, 5, 6 with the 5. 1, 2, 3, 4, 6 with the 6. Okay, you get the idea? So we end up with 6, 6, 6, 6, 6, 6. We get 6 times. So that second die ends up multiplying my possibilities. So the total number of outcomes, this is a tree diagram. I'm not going to list my sample space as S equals set brackets, but I will tell you the number in that sample space. There's another way to represent number in sample space, just being really specific. There are 6, 12, 18, 24, 30, 36. Or you can say there are 6 possibilities on the first die, 6 possibilities on the second die. That tree diagram means I need to multiply. So I do 6 times 6, first die times second die, for 36. Okay, now let's think about the doubles. So there's our denominator, so the probability of getting doubles, which would be double 1s, double 2s, double 3s, 4s, 5s, or 6s. If you go through your tree diagram, you're going to find the double 1s here, the double 2s here. You're going to find 6 of those doubles. Oops, you can't see that. You're going to find 6 of those doubles. So there are 6 doubles up here. So there are 6 doubles in my sample space. I'll circle the first one so you can see them. Okay, there's the first double. There's the double 2s. The double 3s are going to be right there, and so on. So I've got 6 doubles. And the number in my sample space goes in my denominator, which is 36, also known as 1/6. So if you're trying to get out of jail in Monopoly, you need doubles, right? So you're hoping for the odds being in your favor, because you only have a 1 out of 6 chance. Let's follow up this tree diagram with a tree diagram for the coin. The coin's actually a lot simpler to look at. So if I get, actually I've got room here. So let's do the coin. So let's say that we toss 2 coins. Toss 2 coins. So for the first coin, I could get heads or tails. So much easier than the die. For the second coin, I can get heads or tails to match with heads, heads or tails to match with tails. I can list the sample space. It's not too big. So my sample space then becomes, I read down the branches, heads with heads, or heads with a tail, tails with head. Notice how that shows up twice. It's more likely, because it can show up twice, or tails with tail. Now I can ask a question like, what's the probability of getting at least one head? Let's see, this one fits the bill, that has 2 heads. This one works, it has 1. This one works, it has 1. Just that one doesn't. So I would have a 3 out of 4 chance. Look at that sample space, the number in the sample space. There are 2 possibilities for the first coin, 2 heads or tails in the second coin. That 1, 2, 3, 4 is the same as multiplying those together, 2 times 2. So sometimes you don't need the tree diagram or the sample space listed out. You just need that denominator, and you can multiply those outcomes together. Okay, the last few examples that we did all were theoretical probabilities, and that's because we were using this favorable out of total. In the next example, we're going to use an empirical probability. It's going to feel a lot the same. You're just not going to see that fraction show up like it did in the last few. So this one's called empirical because we're using data instead of using favorable out of total. So this one says, in a survey of 1,000 adults statewide, 526 people attended at least some college. Part A, if an adult in the state is selected at random, what's the probability that he or she will have attended some college? Well, we're basing it on our survey. So what we're finding here is that the probability of a person having some college, based on our survey, is 526 out of 1,000. And if I divide that down, that would be 52.6%. With these empirical probabilities, let me spell that, R-A-C-A-L. With these empirical probabilities, if I spelled it right. Anyway, with these empirical probabilities, since it's data, percentages seem to make a little more sense. We're talking about a number of people. 52.6% makes more sense than the 526 divided by 1,000, or even what that fraction would be simplified. Okay, so if an adult is selected at random, what's the probability that he or she will attend some college? We already did that. The probability that one person selected at random will attend some college, based on our survey, is 52.6%. You could do 0.526, you could use the fraction, but the percentage is the most meaningful here. What's the probability that this person hasn't attended any college? Okay, well, think about it. 526 people said they did, which means that the rest said that they didn't. Those 2 percentages. So the probability no college is going to be the rest. 100% would be everybody. We're going to subtract the 52.6% who did. And when we do that subtraction, what we're doing is called the complement. We're starting with everybody, and we're subtracting what we don't want. This is called the complement with an E in the middle. Complement. And we end up with that complement as being 47.4%. So again, to do a probability using the complement, you don't even need to know that word. I'm not going to ask you to use a complement. You just need to know that you can do 100% and subtract what you don't want. And then you end up with the probability that you do. Okay, part C. 2 adults are selected at random. What's the probability that they both have some college? So this is the probability of college and college. When we use that and in the middle, we end up multiplying. So and means to multiply. In our tree diagrams, we multiplied 2 times 2 to get 4 possibilities on 2 coins. We multiplied 6 times 6 because we're rolling the first die and the second die. We're tossing the first coin and the second coin. So we multiply the outcomes together. Same is true here. So I do these probabilities separately. So this is the probability that the first person has gone to college times the probability that the second person went to college. So I'm just multiplying those together, and I end up with, let's do the decimal form to start. So we get 0.526 times 0.526. College and college, we multiply those together. 0.526 times 0.526. And we end up with, I'm going to put this back into a percentage. I get 0.27. I'll call it 0.277. So let's call that 27.7%. So college and college. The next one, the last one, what's the probability that neither have had any college? So now I want probability of no college and no college. I'm going to multiply those together. So this is the probability of no college times the probability of no college. Well, we already did the probability of no college. That's this number up here. I'll use 0.474. So I multiply those two together, and we get 0.474 times 0.474. Or you can take that to the second power. 0.474 times 0.474. And this probability is about 0.22225, or how about 22.5%. So I think these empirical probabilities are easier because I use those percentages, and I don't need to figure out how many are in my sample space. I'm just basing everything on these percentages. So that's the empirical probability. Let's see, one more example, and the last example is with a deck of cards. This is a standard deck of cards. You should be familiar with a standard deck of cards. If you don't have a deck of cards, I'm sure you must know someone who does. You can go to the dollar store and buy one. This one's from a casino in town. I do not go to casinos, but I ended up with one anyway. Just a standard deck of cards. So first of all, there are 52 cards in there. So if I happen to be looking at one card, like I am in Part A here, N is 52. What's the probability that it's a heart? Well, in my deck of cards, I have hearts, I have, what are the spades, I have diamonds, where's a club? And there's a club, and I have clubs. So there are 4 suits. So a fourth of the deck are hearts. So let's see, so 1/4 of 52, that would be 26. So there are 26 hearts, 26 spades, 26 diamonds, 26 clubs. Okay, so you can figure out the deck of cards. So one card is selected at random. What's the probability it's a heart? So the probability that my card is a heart is, well, how many hearts are there? There are 26 out of the 52. If I divide that down, and here's how you can do it. So if you don't recognize, oh, did I say 26? Sorry. How about 13? How many people caught me on that one? How about 13? That was half the deck. Okay, so how about 13 out of 52? So 13 of each suit. So you can divide this down, but if you're not good at dividing it down, or if you don't recognize that it should be 1/4, your calculator will simplify these for you. So I'm going to hit clear just so you can see what's going on better. And I am going to, in my calculator, I'm going to put in the 13 over 52. You can hit enter. I'm not going to, though, because I'm going to do one more thing. I'm going to go to the math menu, which is right under alpha. So I'm going to go to math menu. The very first choice is convert to fraction. Well, it doesn't just convert it to a fraction. It converts it to a reduced fraction, which is awesome. And then I hit enter, and it changed it to a 1/4. So that's a really, really great way to reduce some of these fractions. And your book will reduce all of the fractions. Okay, so let's see. So we got that figured out, right? 13 in each suit, not 26. And we reduced that 13/52 to 1/4. Okay, what's the probability that it's a 10 or a face card? The face cards are the jacks, the queens, the kings. There are 4 of each, because there's 4 in each suit. Oh, look, mine's already in order here, more or less. So if I figure out how many face cards there are, so for the kings, there are 4. The queens, there are 4 of those. The jacks, there are 4 of those. So these are my face cards. And the 10, because there's 1 per suit, there are 4 of those. So as I do my favorable, so 10 or face card, I want my favorable out of my total. I've got 1, 2, 3, 4, so that gives me 16 out of 52. And I'm going to do this in my calculator again. I'm going to go 16 divided by 52. Oh, not 13. I'm going to go 16 divided by 52. Math, convert to fraction, if you can see all that. And then there it is. So I get 4/13. So it reduced that for me. I don't know if you could see that, but you should be able to do that also. So 4/13. You could also do the percentage. That would be fine too. What's the probability it isn't an ace? Well, I could count up all the ones that aren't aces, or, and I hope you've already done this, there are 4 aces, yes? So that means not aces, and I think you'd figure this out without me even writing anything down, are the rest of them. This is that same complement idea. So I'm going to start not with the aces. I'm going to start with what I don't want. So I'm going to go 52 minus 4, and that would be 48. So not an ace, there are 48 cards that aren't aces. So the probability that it's not an ace is 48 out of 52. And I'm going to do, again, 48 divided by 52. Math menu, I'm not showing you this time. Convert to fraction, and that reduces down to 12/13. Okay, so that was all for 1 card. Now we're going to select 2 cards at random. So that word "and" is going to show up again, because the probability that they're both kings, you're going to think of this as a king and a king. So I'm going to take my deck of cards here, and I'm going to select a card at random, and I want to know these probabilities. And you know what? Let me break this up again so you can follow it through. So I want the probability of a king, and means multiply, times the probability of a king, with replacements. So I'm starting with 52 cards. When I draw that first card, there are 4 kings out of 52. To make the probability work, since it's theoretical, I assume the first card that I draw is a king. Well, actually, it doesn't matter in this one, I guess. Okay, so there it is. So there's a king. There are 4 of them out of the 52. But I want a king and a king. But with replacement means that I put this card back in the deck, and there are, again, 52 cards in this deck. So when I figure out the probability of getting a king again, there are 52 cards, and there are still 4 kings in there. And then I draw my second one, and it's not a king. So to figure out what my answer is here, I'm going to multiply this together, and I'm going to let my calculator do the work, especially if there's a fraction in the back of the book. And I'm going to go, I'll use parentheses, 4 divided by 52 times, you don't need the times, 4 divided by 52. Math, convert to fraction, and we end up with 1 over 169. And again, you can do, let's do 1 over 169. You can also use the decimal form or the percentage form. I'll put all those up here. So my answer would be 1 out of 169, or 0.0059, or move that over twice, 0.59%. Okay, a really, really low percentage. So that was with replacement. We put the second card back, so there were still 52 cards. Now let's do this one with replacement. So if I'm doing this one with replacement, I'm still doing I have 2 balls, 2 cards. 2 cards at random without replacement. What's the probability that they're both kings? Okay, king and king. King and king means to multiply. Probability of a king times the probability of a king. So I'm going to do that first king. There are 52 cards here in my deck. So I've got 52 cards in my deck. And there are 4 kings in here right now because all the cards are there. So there are 4 kings out of 52. But now I'm not going to put that card back. This is a lot more practical, because when you play cards, when you're playing blackjack or poker or whatever, you don't get one card and then put it back in. Everybody holds on to their cards, and those cards aren't replaced into the deck. So you can see how these get more complicated. So there are 4 kings in there out of 52. To do my theoretical probability, I assume that the first one I draw is a king. Okay, so it is a king. I don't replace it, though. Now I do the second probability. Okay, so I do the second probability. Here comes the second king. I assume that the first one I drew out was a king. How many kings are left in this deck? Okay, there were 4. I took out 1, so there's 3. How many cards are left in the deck? For the cards that are left in the deck, I took 1 out. It's over here, which means there are 51 cards left in the deck. So I end up with 4 out of 52 times 3 out of 51. I end up counting down. And if I go ahead and multiply that out, I get, let me put this in here, 52. I'm just going to give you the decimal form. 0.0045. Let's do, just for fun, the probability of 3 kings. 3 kings. So this would be the probability of a king, king, and king. I'm going to do those 3 probabilities. I am going to draw the first one. And remember, I'm always assuming that I'm drawing kings to make it work out. This is also without replacement. So as I draw the first king, put it up here. So as I draw that first king, all the deck is here. So there's still 4 out of the 52. I assume it's a king, so I want to figure out the probability of getting all 3. So I assume the first one's a king. There it is. Now I want to draw a second king. Okay, how many kings are left? There were 4, so now there's 3. How many cards are left? Out of the 52, one's over there, so 51. Okay, I assume the next one I draw is a king. I set it up so it would work. There it is. So for the last one, how many kings are left? Okay, I drew 2. That means there are 2 kings left. How many cards are left? Out of 52, 2 of them are over here. We're not putting them back, so there are 50 cards left. Okay, so let me put this in my calculator. Again, I'm just going to give you the decimal form. Likely or unlikely? Like really unlikely, right? So let me multiply this out. Notice how huge that denominator is getting on us. And I end up with this as my answer. I get 1.8, 1, I'll round it, e negative 4. Okay, let me show that to you. This is the calculator's scientific notation. This does not fly, because this is just TI-84 scientific notation. This isn't like the math world scientific notation. This is just the way your calculator shorthands it. So you need to write it down mathematically correct. So this is 1.8 e negative 4. This means that there are 4 decimal places, or 4 places after that decimal before you get to the decimal here. So I'll show you. So as I put that together, it would be the same as 0.1234, and then I pick up where that decimal was. So now I'm at the 181. Okay, so very, very small. You don't need to convert it this way. All you need to do is to change their E notation into scientific notation. So all I'd want you to do, you don't need to worry about getting it into a decimal form or a percentage even. You can just write this as 1.81. The E is times 10 to the negative 4. That would be your answer. So change that E into times 10 to the negative 4. That answer won't work. Okay, so that is probability. So we've covered several different types of probability: theoretical, empirical. We looked at the word or when we were really just counting the possibilities. You can think of that as adding. And then we also focused on the word and.